then you can download the file like this. Save it. Then if I edit it on my computer, so I'll just okay. Now, the way you do this, it says upload via web dev. I don't know what web dev is, and I don't know how to use that, but what you can do is you can literally, oh, I closed it, didn't I? Let's open it again. I can just like, I just like copy pasted the entire file, right? And then I can paste it into this pink box, and then I go in here, and I can paste into here, so you can see a couple of it. It's a little annoying, but I mean, yeah, I guess because it's like, it's not just like a web app that someone made, it's like an entire VM running inside of a container in a web page, right? Yeah, I guess just like the process of like getting stuff in between it is, because it's like, it's in the sandbox, it's like kind of makes the, does that help?
Yeah, I was clicking on the file, trying to like...
Oh, yeah, no, exactly. Well, that's what I was doing at first too, because you're like, yeah, I want to save, right? No, but this is the file menu
for
like
the computer that
for the like virtual machine,
yeah.
right? So like, this is just Emacs running inside this virtual machine. And when you say file stuff, it just looks on the file system, which it just looks normal, but it's like, it's all virtual. Yeah, no, exactly. So, I mean, you can have multiple files in this like virtual file system. You can, but yeah, it's the magical thing on the bottom. All right, anything else? Anything else in particular you going over? All right. So, what I wanted to show you, and again, this is just for fun. There's not going to be anything about this on a module, except for the fact that since we're doing Agda stuff, like it may generally help you be more familiar with Agda as you're doing your module. But I'm not going to ask you to do anything as complex as what I'm going to show you. But just a fun example of the kinds of things you can do with a dependently typed language. And to kind of tie together some stuff we've done before. What I want to do is encode the simply typed lambda calculus in Agda. So similarly to how we've, I've asked you like to write some Haskell functions that'll say find all the free variables, or, so like we've written down a data type to represent lambda calculus terms and stuff like that. So we're going to do the same thing in Agda, except we're going to give them much more interesting types. So that basically, in Haskell, when we made a data type represent lambda calculus terms, it's very possible to write down a lambda calculus term that's a valid Haskell data type, but wouldn't type check in the lambda calculus. Like it's like not a valid lambda calculus term, right? But we can actually write down some interesting types in Agda so that it's not possible. Like the only things you can possibly write down that Agda will say is okay are lambda calculus terms that are actually have valid types. And then we can actually write like an interpreter that will actually run them and give you back, whatever. If it's supposed to give you back a natural number, it'll give you a natural number. If it's supposed to give you back a function, it'll give you a function. And so on. Whereas in Haskell, if we were to write an interpreter, we'd have to make up some new like value type, and it'd say, well, it returns you something of this made up type that we made value. But in Agda, we can actually no, it actually gives you an Agda natural number or whatever. So that's the goal. And let me show you how to do this. So the first thing that we need is, we're just gonna write down a data type for, Lambda calculus types. So, I'm just gonna call it tie. This is, why is it gray like that? There we go. Alright, so we're gonna, the simply type Lambda calculus we're gonna write down, basically, we're just gonna say it's got, natural numbers, and it's also got functions, of course. So, I'm gonna write that, write this double equal arrow. Okay. And the levels definitely get confusing because we're encoding a language inside of a language, right? So, this data type tie represents types in our simply type Lambda calculus. But of course, Agda has types too. So, anyways, this makes sense so far. What we're doing. Okay. So for example, one type we could write down would be like nat arrow nat. So that would be a possible type, right? Or we could say like nat arrow nat arrow nat. If we wanted, we could add more base types and stuff, but this will be enough to illustrate the ideas. Let's say this is infix. So we can write let's make this. So just so we don't have to parentheses everywhere, I specify, hey, it's right associative and it's precedence. All right. The next thing we need, so I could, if I was doing this in Haskell, probably the next thing I would do is write down like a data type for terms, right? So, and I would just say, a term is a set where, and then I would say, well, we have application, which has a term and a term, and stuff like this, right? I would say something like, variable is like a string to a term, and lambda is like whatever, right? The kind of thing we would do if we were doing this in Haskell. Okay, but I want to be much more fancy than this. So a term is actually, like the type of a term is actually going to tell you what its type is in the Lambda calculus. And we can't just have a type because the term might also have variables in it. So we also need a context, right, that says, in this context, this term has this type, just like we would write down a type of goal. So that's going to be our goal. I want to be able to say something like, I'm going to say something like, term actually takes two arguments, a context and a type. So I wouldn't just say like term by itself. I would have to say term, in some context, gamma, and some type like, that or something like that. Okay? So that's where we're trying to get to. So what do we need? So we need to first define contexts. So I'm going to make a data type for that. And a context, the context basically is a list of types, right? Well, it's a list of variables with their types. The way we're going to do it, we're just going to make it a list of types, and instead of variables being names, we're just going to make them like numbers that index into the context, right? So like, the variable 2 just means like the second thing in the context. So in order to make that work, the context is actually going to have a natural number that tells you how big it is. Because otherwise we don't know like what would be a valid variable for this context. Because if the context has 3 things, I don't want to have the variable 5 because it's going to be too big. So the context is going to say, all right, so what are contexts? Well, remember a context basically is either empty or it's like a context with an extra thing added on the end. Right, so I can say, I'll use the empty list symbol some n, if you have a context n, comma, a type, that'll be a context n plus 1, because it's one longer. And let's also make a this. Try that. So let's just do an example. Context n. Let's make a context 3. So for example, if I just try to say empty list, it shouldn't work because it says, oh, it's too small. Let's make this bigger. Oops. It says 0 is not equal to 3, right? Because I gave it a context 0 and it wanted a context 3. So I have to put specifically 3 things in it. So I could say empty list, comma, let's say tie1, comma, tie2, comma, then I'll just put nat on the end. Okay, and that it accepts, right? So this is a context with 3 things in it. There's 3 variables named, 0, 1, and 2 that would correspond to, the first variable has this type, the second one has this type, and the third one has this type. Questions so far? All right. So now, I think I can actually start writing this down now. So, actually, before we do that, I always forget that. Let's make a lookup function for the context. So if I say lookup, I'll call lookup C for context. I basically want to give this something like, this is not quite right, but I'll just illustrate. Right, so it's something like, I'm going to look up, I give a natural number, which is the number of the variable I want to look up, and I give a context, and then I give a type. However, this is not going to work. Anyone know why? We're not going to be able to define this in a way that Agda is going to be happy with. Anyone have an idea why? Well, I'll give you a hint. Right, a type is basically a promise. So this is saying we're promising that for any natural number and for any context of length n, whatever n is, we can give you back a type. Right, what might go wrong with that promise? It should be out of range. Exactly, it could be out of range, right? If the number is too big, then we're not going to be able to return a type. And you could say, well, maybe we'll just, if it's out of range, we can just use the last type in the context and just use it. But, the context might actually be empty. It might be 0, right? So, we can say maybe type, because that's going to be super annoying. And that's not really what we're going to do. So, what we're going to do, instead, we're going to use a type called data.fin. And fin, I'm not going to show you the definition, but I can just use an example. So with natural numbers, I just have natural number type. But fin takes a number as an argument. So for example, fin3 is a type that has exactly 3 elements of that type, 0, 1, and 2. So anything bigger is not valid, right? So fin5 has 5 things in it, 0, 1, 2, 3, 4. So for example, fin5. So for example, I could say 0, and that would be valid, right? And let's make it smaller. I could say suck0, that would be valid, right? It's okay with that. I could say suck0, that's okay. But if I try to say suck0, it's going to give me an error. It doesn't matter what the error is. The point is only valid, up to that size. And that's exactly what we want, right? Because if we have a context of length n, then we want to only be able to provide, things up to that size as indices. So we can, no, I'll do that. So what I want to say here is this is not any natural number. This is a fin n specifically, or whatever that n is. Okay. So now we know that whoever calls this has to provide a valid index for the context, right? So let's see how to implement this. It's going to be very easy. Call this gamma. As usual, right? Well, I don't know what to do at this point, so I can pattern match. So look, what do you want to pattern match on? Let's pattern match on the I, actually. It turns out that's going to work better. Okay. Now here's the thing. So because this is 0, right? So 0, if this is 0, this has to be like at least fin 1. Right? Fin 0 doesn't have any elements at all, not even 0. So if the first argument is 0, then n has to be at least 1. And Agda can figure that out. And so that means this context, since it's a context 1 or bigger, it can't be empty. And so if I pattern match on the gamma, it's like, yeah, it actually has to be like a comma thing. It's got some context and then the last thing in context. So if I'm looking up 0, then I just want this last thing. I guess maybe before I said the things in the wrong order. It's the thing on the end of the context that's 0, because that's like the most recent thing that you put on here. And then as you count higher, you're counting like backwards farther in the context. Okay, and then same thing here. I can pattern match on gamma. And in this case, right, the variable is successor of something, so I don't want this last thing in the context. I can ignore that, and I just want to keep going and look for, I just want to look up since I'm trying to look up the successor of I thing in this context, I just look up the I thing in gamma, and it'll just keep going down by 1 until it reaches the thing it's looking for. So this is just lookup C. Maybe I shouldn't call this X, I'll call it like T for type of that. Or call it alpha for type. How about A? We often use like, cool. So now, what I want here is, I'm going to say, okay, so there's some n. I'm going to take the context n and the type. Okay, and let's think about it. So there's like var, there's you have a literal natural number. Let's do that first, actually. Start with really easy ones. So because we put natural numbers in our language, so we can just have like a number. I think I'm going to add like numbers that we can have plus. So you can add numbers. Just so we have something to do with our numbers. And then we'll have, application variables, lambda. So if you have a literal number, that's easy. It's just, well, it contains a number. And this will be, what? So we have to say this is going to construct a term. But what kind of term, right? Term, you can't put by itself. It has to have a context and a type. So if I have a literal number, the context doesn't matter. I could have any context I want, right? And so, okay, I need to put here, like, so right, for any n in any context I want, this will be a term in some context, doesn't matter, and it's going to have type nat, of course, because it's literally a number. So that's how I write that. So the interesting thing here, right, is that in Haskell, if we were writing this down, we would have just written it with like, lit is a term. And then the fact that it has type nat, we could write some separate function to infer the type or something, which you all done in a module. Here we're building in the type kind of into the way it's defined. And that's going to mean like it's not possible to write down things that don't have the right type. So if I say I want to write down a term nat, then I could use lit. But if I say a term of some function type, then I can't use lit because it won't have the right type. Okay, let's do plus. I'll make it like I'll use like this circle plus symbol. Right, and this is going to say actually, you know what? I'm going to make this a little simpler. I think we can. Because these kind of aren't going to change ever, I can sort of, yeah, I can put those over here, and that means I don't have to relist them every single time. They're just kind of in scope for the whole thing, because I put them to the left. Don't worry about that. But basically, this just means, look, I just am going to have this parameter n and this parameter gamma that are just parameters for the entire definition. I think this should work. Okay, so plus, of course, takes two terms, right, the left and the right hand side, and they both have to have type nat, and then the whole thing is going to have type nat, right? So let's say it takes a term in any context that has type nat, and a term in the same context that has also type nat, and then this whole thing is going to be a term in that same context with type nat. Okay. What do you want to do next? Variable. We have variables, function application, and Lambda.
Variables.
Variables. Okay. Let's say a variable. And a variable. So a variable, we said, is just going to be represented by a number. So it's not going to be like a string name. It's just going to be like, we have this context with n things in it, and we're just going to have a number that says, how far into the context do you count. So that means I need a number here, but not just a nat, right? Because I want it to make sure that it's like not too big to fit in the context. So it's going to be one of these fin things, right? So it's going to be like a fin n. This is going to give me a term in some context gamma. And what type does it have? So how do you know what type a variable has? Like in general, if I'm type checking something in the Lambda calculus and I see a variable, how do I know what type it is? If you've done the infer type function on module without module letters, right? How did you, when you got to the variable case, what did you do? Same?
How do we call what a schema?
Right, exactly. To know the type of a variable, you look it up in the context. That's what the context is for. And so yeah, this is again, this is something we could not do in Haskell. But I'm writing down the type of something, but I can literally call a function in a type to kind of compute for me the right type that I want. So I can just say lookup C. The type of this variable is, well, look up the variable. I guess I have to give this a name, so I have to call this so that I can refer to it here. Lookup I in gamma. To reload. That's it. Okay. the rule for application, the gamma doesn't really change, it's just like copy for everything. But what types should go here in these holes, right? So in general, how does the type of application work? Like what kind of type should go here? What kind of type should go here? Just for fun. So we can actually write like something dot something to the application. We can't write it with a space because we're not allowed to redefine space in Agda, but just make it a dot. But if I have one term applied to another term, what can I say about their types? One has to be a function type. Yeah, the first one has to be a function type, right? So, we would say something like A arrow B. And I'm using this double arrow because it's not an Agda function type, it's just like our made up functions for the length types. And of course I have to, okay, what are A and B? So I'm just say, well, those could be A and B could be any types. Okay, so if that first term has type A arrow B, then what type does this term have to have? A. And then what type will the whole application have? B. Okay. Now let's do lambda. So, so we can't actually call it.
Like a person.
Yeah, we can't actually call it lambda because lambda is one of the few symbols that is like a reserved symbol in Agda. It's for actually making real lambdas, so I can't name something like that. But people often use this. It's like a lambda with a little bar through it, or maybe it's a little person. Yeah. It's called lambda bar. Is there an easy way to write that? I don't remember. Oh, you don't mind, so cool. All right, well, let's think about this. So, when I write down a lambda, so I'm not gonna make you all come up with this because this one is a little tricky. It kind of depends on the way we've been encoding context and stuff. Normally, I would write down like the name of a variable and maybe a type for that variable at the bottom. We're not using names for our variables. So basically, when I write down a lambda, I don't have to give a name at all. But it's basically going to just like, I have to give a type, and it's going to add that type to the context. And from then on, well, you'll see in a second how we refer to it. But basically, well, every time you write a variable, it's really just a number. And the number is like, how many lambdas out do you count to figure out which lambda it's talking about. So if I say like lambda x dot x, in this I'm just going to write like lambda 0, because the 0 means like that right there. So I have to give it a type. That's the type of the argument. And then the body is going to be something of some type B. Okay, so A and B are terms. And then I'm going to get, well, if the input has type A and the body has type B, then the whole lambda has type A arrow B, right? And then what goes in that question mark? Well, that's the context in which we need to type check the body. And that's this gamma, but we also add the type A because we now have this extra variable that the body can refer to. So I just write gamma, comma, A. So, let's write down some terms. Let's make some term in an empty context that has type, nat. So I could just say, lit 3. That should work. Right? Or I could say like, okay, another term that has type nat would be like, you know, I could apply a lambda. So the lambda that takes a natural number and returns. So like I'm gonna write like lambda x dot x. So this is like lambda x dot x applied to 3. So the way I write down lambda x dot x is I say, well, it's a lambda, it takes an argument of type nat, and then it's going to return x, but I can't write the name x. I have to say, in this case, I say 0, because it means just like the innermost enclosing lambda is one that I want. And I want to apply this, so the application I write with the c dot, little dot there. And then we're going to apply it to lit 3. Right, because yeah, 0 has type. It's like one of those fin things, but I actually need a term, so I need to say var to make a variable. Yeah. So that's cool with that, right? And if I try to write down something like what if I try to write down something like lambda x dot xx, right? So this should not be possible. Right, even if I say, I don't know what type it's going to be, let's just see. So it takes we'll say it takes a nat. Well, I mean, I even have to say like what type it's supposed to take. But if I like, I don't know about that either. But it's going to be an application of var 0 to var 0. Even with those question marks, right? It's like, I'm not sure this is going to work. So I'm not going to be able to fill these in with anything that's going to make it work. And it's even before filling those in, it's like I had this constraint, and if you squint at this, forget about the fact that it has a bunch of underscores and numbers, right? Basically, it's saying I had a constraint that says a arrow b is equal to a. Right, and that doesn't make sense. There's no a that would solve that. And that makes sense, right? Because we saw before, if we try to give it a type, we kind of end up having to give it an infinite type, because x has to both be a function and it also has to be the right type of input for itself. So the point is, there is no way I can actually write this down. Okay. So, so we could pretty easily, we could add other things, like we could add pairs, we could add, meters, we could add, and you're kind of just like encoding the typing rules for those things in the data type itself. Let's see if we can write an interpreter. Tell me about it. So my goal is to write an interpreter that takes a term in empty context for some type A, and it's going to return, well, it can't return A. That doesn't make sense, because A is one of these, it's just a data type tie, right? Agda doesn't know what that means. So we're going to write a function that also interprets types, basically turns one of those types into a corresponding Agda type. So like the type nat is going to turn into actual Agda type of natural numbers. And the type, A double arrow B will turn into actual Agda function type. So that's our goal. Let's write this interpret tie function first. And it takes one of our values of this made up type tie, and it returns an actual Agda type. This is set. And this always, I don't know, somehow this always blows my mind. If you have a type that just like computes types, or a function that computes types. So yeah, no problem. So, well, let's write it. So pattern match on T. Okay. Nat is going to correspond to the Agda type. Numbers. And we'll call this A arrow B. correspond to the actual Agda, function type. And I also need to recursively interpret A and B because they're also ties, right? So tie A, tie. Okay. Yeah, it looks so weird to me having the output of a function be, a type. But remember, in Agda doesn't make any distinction really between types and terms. Everything is just terms. And, some terms can go on the right of a colon with other terms in left of a colon. Just like they have this relationship that's like something is a type of something, but, you can totally have functions that take types as arguments or return types as, so just like in Haskell, like functions are first class, and compared to some other languages, that's like, oh, that's cool, and, functions you can just do whatever with. Well, Agda takes that, way further and says, no, types are first class, right? So you can have functions that compute types.
I'm imagining a function that's like similar to this in Haskell, where you would say inter function name 0 equals like integer or something, and like.
Right. Yeah, no, you can't do that in Haskell.
Yeah.
I mean, you can kind of fake it using some more advanced language features that we haven't talked about, but like it's very awkward and it doesn't, it's just like a bunch of boilerplate. Okay, so the point now is that right. So let's start running this, and we're going to get stuck, and so then we'll see what we do. Try to mention that. So lit x, let's see what it says. It says, hey, you have to put something in the hole of type nat. And how did it know that? Well, because we said the type of lit x would be a term nat. And then it interpreted that into an Agda type, and it said, yeah, you have to. So that's easy, like we have x, it's literally just x. X plus y, well, we can just recursively interpret x and y, that'll give us actual natural numbers, and we just actually add them in Agda, right? So we can say interpret x plus interpret y. Easy peasy. For x applied to y, well, if I interpret x, I'm going to get something which is the interpretation of this type, right? But the interpretation of this type in Agda is an actual function. So I'm going to get an actual function out of x, and I'm going to get something of whatever type y is, and then I can just literally apply them, right? So I can say interp x applied to interp y. Here's where we're going to get stuck, though. Because here's the problem. I want to somehow say, like, well, I'm going to return an actual Agda lambda, and then I'm going to recursively interpret t, and, kind of return that. The problem is, this interpretation function says, well, it has to take a term with an empty context. And this t does not fit that, right? It doesn't have an empty context. It's got an a in the context. Because it's a lambda, that takes an argument of an a, right? So this t, can have this extra variable that it can refer to. So if I try to just, like, recursively call interpret on t, it's not going to like it. So, yeah. It's like, yeah, no, those don't have the right, those don't match. So the thing we have to do, and I honestly don't know if we have time for this. super rushed, and it's not really gonna make sense, or we're not gonna finish anyway, so. Tell you what, I'm just gonna like tell you what we have to do, just like at a high level. And then probably maybe this afternoon, I'll finish typing it and I'll post it so you can, if you wanna go look at the actual code, you can. The idea is not too hard. The actual code will just take a little bit of time. So the idea is, well, when we're interpreting a term, right, we could have some variables around. And when we're type checking a term, we have to keep track of the types of variables. When we're interpreting a term, we have to keep track of the value of variables, right? So, you know, if I'm interpreting something and I come across the variable x, I need to know what value is x supposed to have right now. Okay? So we're going to make something called an environment that looks very similar to a context, right? But a context has a bunch of types in it, and an environment is going to have a bunch of values, okay? But values of what type? Well, it depends on the context. So the environment is actually going to have a context as part of its type. It says, well, I have an environment for this context, meaning it has to have values whose types correspond to the types in the context. And then when we see a variable, and you notice it didn't actually give us a case for variables, but that was because we said it was a term with an empty thing here, and so that can't possibly be a variable. So it said, oh, you don't have to do that case. But we do want to generalize this and say, well, we can do this for any context, but we also have to add an extra argument that says we need an environment too that kind of corresponds, so that when we see a variable, we can just look it up in the environment. And when we interpret a lambda, we're going to say, all right, we're going to make an actual Agda lambda that takes an argument, and then recursively interprets this t, but it's going to add that argument into the environment. So just like, you know, if you were writing an interpreter in Haskell, you might make a recursive call and say like m.insert, you know, some value into this context, right? But it's going to be a very kind of similar thing, where we're inserting an extra value into the environment. That's the idea. And, you know, just getting the details right in terms of like, well, you know, the environment has a context in its type, and then you've got to like interpret the types of the context to get the types. It's just a little bit of work to get it all to line up, but conceptually that's all of it. So we need to pass around an environment of values. So that would be it. And, you know, and you can actually play this game with much more complicated languages. Like I said, we could, like actually like getting lambdas and applications and stuff like that and variables to work is really the most interesting and difficult part of this. So like if you wanted to go and add, you know, like pairs, you could have like a type, you know, just like the Haskell type A, B. You could add add that to our tie definition, and then add like you know, a kind of pair thing here, like a first and second. It wouldn't be that hard to add. It would all, once you kind of wrote down the right types for it, like the interpreter and stuff would kind of write itself. I mean, Agda you could almost just do auto in it, just fill in the interpreter for it. So anyway, I mean, this is like, you know, is this of practical use? I don't know. I mean, if you really want to study languages and encode them, I guess it's kind of. But no, I mean, so this, I'm not showing this to you because it's because you will practically use this, but it's just an interesting example of the kinds of rich specifications that you can encode in this, you know, in Agda, and have it kind of automatically check that you can only write down valid things. All right. Cool, that's it. So, have a good spring break. See y'all later. And, you know, I'm going to be around over spring break. Don't, I mean, you can't sign up for meetings, but you can definitely feel free to email me with questions or send a message. I may not respond like as quickly as I normally would, but don't feel bad. If I have a